know or what we usually we observe some symptoms. And based on the symptoms, if we want to predict the disease, then this problem we can model using the hidden Markov models. So let's say one of the problem we can model here is the weather prediction model. Specifically, if you can consider that we just observe the rainy day or maybe dry day, whether today is the rainy day or maybe today is the dry day. So we can observe that there is rain or maybe dry. So this is the observation. That means whatever we can observe, but we can see. But we don't know about the atmospheric pressure of that day, whether the atmospheric pressure is high or maybe the atmospheric pressure is low. We don't know about that. So those are hidden from us. So those usually we can consider those are our hidden states. Hidden states. So those are our hidden states. And just we can observe the rainy day or dry day. But if you apply the hidden Markov model, then we can predict that whether, based on the observation, whether today is a dry day or maybe the whether the atmospheric pressure is high or maybe low on that day. Okay, so that means based on observations we can predict the states, though the states are hidden. Similarly, think about another example like dishonest casino model. The casino player maybe use the loaded die or maybe fair die. Okay, the fair die, maybe we can say this one is fair and this one is loaded, unfair, okay? Loaded. What we can see just only the observations. These are the observation sequence. So sometimes this casino player use the fair die and sometimes the loaded die. Loaded, that means unfair, okay? Loaded on 6. Okay, every time C is to get the 6. Okay, so that is our loaded die. So sometimes maybe the casino player played and we observe that, okay, just one appeared, okay? We can see just one. And second run, second play, we observe just 2. Third play, we observe 4. In this way, maybe we observe that this 6, and then again 6, and again 6. Okay. So those are the observations, just observations, but we don't know whether the casino player, the dishonest casino player, sometimes use the fair die, sometimes the loaded die. Okay. Then we want to know that is when the casino player used the loaded die and when the casino player used the fair die. So that means we can just observe the numbers here, but there is the types of the die, those are unknown to us, okay, hidden to us. But if we can model this problem using our hidden Markov model, we can predict that for this observation, whether the casino player used the loaded die or the fair die, or even the sequence of, okay, maybe for generating this sequence, what's the most probable sequence of die used for that? Maybe this observation from the loaded die, this observation from the fair die, and the next observation from the loaded, next observation from the fair, and then again maybe fair, and then maybe loaded, like this. Okay, so that means based on the observation, we want to predict the states that are hidden from us, we can apply the hidden Markov model for that purpose. In hidden Markov model, specifically we need three kinds of probabilities, three types or three kinds of probabilities. Initial probabilities, transition probabilities, and emission probabilities. So three kinds of probabilities are necessary for that. The initial probability of the state, like initial probability of low atmospheric pressure is 0.4. The initial probability of high atmospheric pressure is 0.6. From the data set, if the data set is given, we can find out those probabilities. Then transition probabilities. Okay, we need the transition probability. What's the probability of low to low? And what's the probability of low to high transition? That means we can see this is currently low atmospheric pressure in first day. What's the probability that the next day will be high atmospheric pressure? Sorry, this one. So today, that is in day one or time slot 1, day 1, the low atmospheric pressure. What will be in day 2? If we consider this is day 2, the probability that the atmospheric pressure will be high in next day, it is 0.7. So that's it is written. Currently it is low. What's the probability that in next time slot it will be high? That is transition from low to high is 0.7. Similarly, low to low, that means today is low atmospheric pressure. Tomorrow will also be low atmospheric pressure. For that, it is low to low is 0.3. Okay, so here is the 0.3. Similarly, if today is the high atmospheric pressure, what's the probability that tomorrow will also be high atmospheric pressure? That is 0.8. Okay, so high to high is 0.8. And today is a high atmospheric pressure. What's the probability that tomorrow will also be low atmospheric pressure? That means transition from high to low is 0.2. So here is the point. Transition from high to low atmospheric pressure is 0.2. These kind of probabilities are called the transition probability. Transition probability. Then another probability we need to know, that is called the emission probability. Okay, emission probability. So three kinds of probabilities we need to know in hidden Markov model. Emission probability. So emission probability is this: low and rain. Okay, what's the probability of rain on low atmospheric pressure? So what's the probability of rain? Probability of rain in low atmospheric pressure. So this is the probability of rain in low atmospheric pressure is 0.6. Yeah, this is 0.6. Probability of rain in high atmospheric pressure. So this is the probability. Okay, probability 0.4. So probability of rain in high atmospheric pressure, high atmospheric probability of rain is 0.4. Probability of dry day on low atmospheric pressure is 0.4. Probability of dry on low atmospheric pressure is 0.4. Then probability of dry on high atmospheric pressure is 0.6. Probability of dry on high atmospheric pressure is 0.6. It should be 0.6. 0.6. Okay, 0.6. So this is called emission probability. Emission probability. And we can see that summation of this row is 1. Summation of this row is 1. Summation of this row is 1. Also 1. And summation of these two initial probabilities are also 1. Okay. So that means the emission probability, transition probability, and initial probabilities. So these are the three probabilities we need to know if we want to apply the Markov hidden Markov model. So what else we need to know? We need to know about the number of states and what are those states, and number of observations and what are those observations. Okay, so that means to model any problem, we have to know the states and observations. Though the hidden states are hidden, but we need to know that how many possible states are there. Like here in this problem, the atmospheric pressure, we have considered just only low atmospheric pressure and high atmospheric pressure. That means we have considered the two states, though the states are hidden. But we need to know we have two states. And how many observations we have? Like here, we have considered two kind of observations, like the rainy day and dry day. Okay, so that means we have to know the number of states and what are those states, and number of observations and what are those observations. Like in casino model, if we think about the casino model, we have to know how many types of dice are there. Like here, two types of dice. Die can be fair, die can be loaded. And what are the possible observations? So if we roll a die, then the possible observations are, it can be one. We can that means appear. One can be appeared, two can be appeared, like in this way. 1, 2, 3, 4, 5, 6. 6 possible outcomes from a single die, okay, die roll. So that's why the model will be like this. Okay, so that means the fair and loaded. Then we need to know that is the initial probability of fair die, initial probability of using loaded die. Then we need to know the transition probabilities, the transition from fair to loaded, and then fair to fair, and then loaded to fair, and loaded to loaded, the transition probabilities, and also the emission probabilities. Probability of getting 1 from fair die, probability of getting 2 from fair die, probability of getting 3 from fair die, probability of getting 4, probability of getting 5, probability of getting 6. And if we use the fair die, we can see the probability will be equal for all observations. That is, probability of getting 1 is 1 by 6, probability of getting 2 is also 1 by 6, like probability of getting 6 is also 1 by 6. Similarly, if we use the loaded die, then we have to know the probability of getting 1 in loaded die is 1 by 10. Probability of getting 2 in loaded die is 1 by 10, like this way. But the probability of getting 6 is high here. You can see 1 by 2. That means 50% of the time from the loaded die, we will get 6. And all other observations like 1 to 5 has the equal probability. That is 1 by 10. Okay, 1 by 10. So 5 times 1 by 10, 5 times 1 by 10, that means 1 to 5, 5 times 5, 1 by 10, it is half, okay? So it is half. And getting 6 is half also. So getting 6 is half. The total is 1. Okay, total is 1. So that's why we can see emission probabilities. So these are our emission probabilities. So for the dishonest casino model, we can think about. Okay, now if we can formulate any problem using the HMM, we can answer few of the questions. Okay, the first question is, how likely is the sequence given our model of the casino works? So how likely is this sequence? Like this is a sequence. What's the probability of getting this sequence? So that is how likely of getting this sequence using this model. Okay, so we want to find out the probability of this observation sequence. Okay, observation sequence. And second question we can answer, what portion of the sequence was generated by the fair die, and what portion of the sequence is generated from the loaded die. So if the sequence is, let's say, the observation sequence is maybe you can say 5, then 6, then 6, then 4. So consider this is the sequence. Then we want to know that is the what portion of this sequence is from loaded die. Maybe this 5 is from fair die. This 6 is from the loaded die. This 6 is from the fair die. And this 4 is from the loaded die. Maybe, okay, maybe. So that means we want to know the sequence, know this hidden state sequence based on the observation sequence. So what portion of the sequence was generated with the fair die and what portion of loaded die? We can answer this question. And we can answer also this question, how loaded is the loaded die and how fair is the fair die? How often does the casino player change from fair die to loaded die or maybe loaded die to fair die? This is called the learning problem, HMM learning problem. So that means, okay, the casino player is using a loaded die and also fair die, but how loaded is the loaded die? That means it is loaded towards the 6, but as I already mentioned that 50% time we will get the 6, but sometimes it can be maybe we can say 80% of the time we will get the 6. Sometimes it can be like 25% time we will get the 6. Okay, so that means how loaded is the loaded die towards the 6 or maybe towards any number. So how fair is the fair die? That means whether the die is fair or not. And how often casino player change from fair die to loaded die to fair die. Okay, so we can answer the questions if we model our problem using hidden Markov model. So now we want to, in today's lecture, we want to find out this answer. Okay, this answer. That means based on the observation sequence, we want to find out the state sequence. And for that, we will apply the Viterbi algorithm. What is the most likely die sequence given observed sequence? Okay, we will apply the Viterbi algorithm. And then at first we want to derive the equations of the Viterbi algorithm and then apply Viterbi algorithm to solve the problem. Okay, so this is called decoding problem 2. HMM, I think you will learn more about the HMM in advanced AI. Okay, decoding problem 2. So utilizing the Viterbi algorithm, we want to find out, that is, based on the observation, what will be the most possible state sequence. Okay. Let's say we want to answer the questions of our that is weather model. Okay, weather model. So we have just maybe on first day we observe the rain. Second day we observe the rain, and third day is dry day. So this is just sequence of observations of 3 days. Day 1 rain, day 2 rain, day 3 dry. Now what we want to do, okay. So based on these 3 observations, we want to know the state sequence. Maybe on this day, that is day 1, we observe the rain, but maybe the atmospheric pressure is low or maybe high. We don't know about that. And for this case, maybe second day rain, maybe the atmospheric pressure is high or maybe low. We don't know about that. Similarly, the third day, dry day, we don't know about the atmospheric pressure is low or high. So what are the possible combinations of these 3? You can say 3 days. So we can see there is, we have 3 days, but 2 options. So 2 to the power 3, 8 possible observations we can have. Like on first day, second day, and third day, we can get the low atmospheric pressure, low atmospheric pressure, low atmospheric pressure. Or maybe low atmospheric pressure, then low atmospheric pressure, then high atmospheric pressure. We can think about like low atmospheric pressure, high atmospheric pressure, and low atmospheric pressure. So in this way, we can get maybe high atmospheric pressure on first day, high atmospheric pressure on second day, and high atmospheric pressure on third day. So these are the possible sequences of observation. But which one is most likely? Okay, which one is most likely? That means which of the sequence has the highest probability, highest probable sequence? We want to find out that utilizing our Viterbi algorithm. Okay? Then what actually we want to do? We want to find out the probability of these three states. The state one can be anything like low or high. State 2 can be low and high. State 3 can be low and high, given just observations. So actually, we want to find out this probability. Probability of state 1, state 2, state 3, given observation 1, observation 2, and observation 3. Okay, so observation 1 is what? Observation 1 is rain on first day. Observation 2, that is rain on second day. And third day is dry day, okay? Dry day. So we want to find out the state sequence based on the observation sequence. And actually, we want to find out this probability. But as we want to know the most probable sequence, most, that means highest, or it means maximum. So here is the maximum. Okay, that's why the maximum. Maximum based on what? Maximum based on these states. Okay, so that's why the argument are given here. The argument here is S1, S2, and S3. Since the values of S1, S2, and S3, then which one will provide us the maximum probability? We will consider those sequence as the most probable sequence. Okay. So from here, we can write this based on what? Based on our product rule of probability theory. Okay, product rule of probability theory. So product rule, it means if we want to find out the joint probability of two events AB, then we can write it as probability of A given B times probability of B. So this is called the product rule. Okay, product rule. So that means the joint probability can be written as the conditional probability and our initial probability. So from here, what we can write, if we can write the probability of A given B, it will be probability of AB divided by probability of B. Okay, probability of AB given equal probability of AB divided by probability of B. So here is also same thing. That is probability of, if we consider these three are our A, and these observations are our B. And probability of A given B, it is probability of AB. That means this one, probability of AB, the joint probability of observation and states, divided by probability of B. So probability of B is probability of observations, all the observations. So as we can see, that is, we want to find out the maximum. Okay, so maximum. So no need to compute the denominator. So that means this probability. As you can see, that is, we don't want the actual probability, but we want that which one is maximum. Okay, so whatever the denominator, if we want to find out that is the maximum between two values, then if the denominator is the same, then actually if the numerator value, based on the numerator value, we can find out which one is maximum. It means if we can see a fraction like 2 by 10, and another value is maybe 5 by 10. So we want to compare. We want to compare between which one is maximum. Okay? Which one is maximum? So here, if the denominator is same, so here the denominator is same. So 10 here is also 10. Then just only based on the numerator, we can determine which one is maximum. So no need to find out the denominator. So here, if the denominator is same, so here the denominator is same, then only the based on the numerator, between these two, which one is maximum? The maximum is this one. Okay. Then 5 by 10 is greater than 2 by 10. So that means if the denominator is the same, then just only the numerator we can determine the maximum, which one is maximum. That's why no need to compute the denominator here. So we want to find out the maximum, then only numerator value, that is probability of S1, S2, S3, observation 1, observation 2, observation 3. That one will be enough to find out which one will provide us the maximum probability. Okay, maximum probability. Now, let's say we know that the value of S3. We know the value of S3. So value of S3, that means it maybe the value of S3 is K. So here it is, the value of S3 is K. Okay. Anyhow, we know the value of S3 is K. That means on that case, we need to know about the S1 and S2 because S3 already we know there is K. Okay. So if we know the value of S3, there is K, then on that case, the problem will be that is only we need to know now S1 and S2. So for the simplicity, let's say this part is our V3 of K. V3 of K, where we can V3, why it is 3? Because we have state 1, state 2, state 3, observation 1, observation 2, and observation 3. That is highest number here is 3. Okay, so that's why 3. And as we know the S3 equal K, so that's why here it is K. There it is K. So let's say this is just symbolic representation. Okay, assume that this is equivalent to V3K. So just symbolic representation. Just we can see that shortcut. Here we have just assumed that instead of writing max S1, S2, probability of S3 equal K, S1, S2, observation 1, observation 2, observation 3. Instead of this, we can just write V3 of K. Okay, V3 of K. It means max with respect to S1 and S2, and probability of S3 equal K, S1, S2, observation 1, observation 2, and observation 3. And now we have this part here. Okay, that is argument max of K, and this is V3 of K. So that means the V3 of K is max of S1, S2, probability of S3, K, S2, S1. Okay, this one. Now again, consider that we also know S2. Okay, we also know the S2. Just assume. So if we know the S2, let's say S2 equal I. S2 equal I. On that case, just what we need to know now, we need to know just only S1. Okay, as we already know the I, so here is max I. So now target is to find out the S1, and then the here this is the probability for that case. Now from here, this probability can be written as the multiplication of several probabilities. Okay, several probabilities. How can we write it? So here we can see there is we can write this one as the probability of S3 equal K and observation 3. So that is probability of maybe you can write like observation 3 and S3 equal K. Given 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 S2 equal I, S1, then observation 1, then observation 2 times probability of this part only. S2 equal I, S1, observation 1 and observation 2. Okay, why we can write it? We can write it based on the chain rule of probability theory. Okay, what is it? From the product rule, that is, we can, if we have like A, B, and C, we want to find out the joint probability of 3. Let's say A, B, C, D, something. Okay, let's say A, B, C. Then this probability we can write it as probability of A given BC times probability of BC. So that means joint probability. If you want to know the joint probability of ABC, 3 events, then we can rewrite it as probability of A given BC, and then whatever in given part, we have to rewrite it here, probability of BC. Okay. So then again, this probability of BC we can rewrite as this one is actually probability of B given C times probability of C. Again, utilizing the product rule. Okay, so that means BC here. So we can write B given C, and then what is whatever the given here, that is the C is given here. That probability we have to write there. Okay, that is probability of C. So similarly, here we can. That's why we can write that these are just only the joint probability. So the probability of ABC, we can rewrite this one as probability of CAB. Okay, we can rewrite this because the events, those are in joint probability. So we can shift C in front, and then we can push B in second position, or you can write the same thing. It is probability of B CA. It will be the same. Okay, so that's why here we can from this probability, from this one, S3 and O3 we just consider in front, and then given all other events, S2 equal I, S1, observation 1 and observation 2. Then the given part we have to consider. Given part. Okay? The given part. That's why you can see from here we have written here this part and then this one. And from this probability, again, we can express this probability using the product of two other probabilities. Okay, two other probabilities. Like this probability, we can rewrite as probability of observation 3 given S3 equal K and S2 equal I, S1, observation 1 and observation 2. And another one we can rewrite it as times, that means this one times multiplication of probability of S3 equal K. So S3 equal K given S2 equal I, then S1, then observation 1 and observation 2. Okay, so that means this probability we can write as the multiplication of these two probabilities, again utilizing our chain rule of probability theory. Okay, this one, and that's what we have written here, that is this probability is equivalent to this one multiplied with that one. But now we want to simplify it. Okay, we want to simplify it. So from this part, we can see observation 3 given state 3, state 2, state 1, observation 1 and observation 2. But according to our Markov theory, specifically utilizing our first order Markov properties, then state 3, it will only depend on state 2, not in other states. So the first order Markov properties, based on the first order Markov properties, so this is the first order Markov properties. It means this one, it will only depend on x1, and x3, it will only depend on x2. In another way, we can say that the future will only depend on that is the present. Okay, or you can say day 2's state, it will only depend on day 1's state. Okay, day 2, it will only depend on day 1, and day 3's state, it will only depend on day 2's state, not in day 1's state. So this is called the first order Markov assumption. So utilize the first order Markov assumption there. So here you can see, utilizing the first order Markov assumption, state 3, it will only depend on state 2, not in other states. Okay, so that's why we can write it like this. This probability we can rewrite as probability of state 3 equal K given state 2 equal I, not on other states and observations. Okay, so we can write this probability as this. Similarly, here for this one, the observation 3, it will depend on the state 3, not on other states and observations. Okay, so if we can see the observation 3, it will only depend on state 3, not in other observations or maybe states. So in this case, we can see there is no direct link between observation 3 and observation 2. So that means observation 3, it will only depend on the states. Okay, this is states, not in other observations or states. So that's why this probability we can rewrite as the probability of observation 3 given state 3 equal K. Okay. So now combining all these, what we will get. So here is the max of I. This is the max of I. And then this one, probability of S2 equal I, S1, observation 1 and observation 2. And this is max of S1. So as we know that the max of V3 of K, this is V3 of K. V3 of K is what? Max of S1 and S2. And we consider the S3 and observation 3, where S3 equal K, we know this. Then we assume that this probability is actually V3K. So now we can see for this one, we can represent this one as our V2K. Why? Because here is the S2 and last observation is O2, and we know the S2 equal I. And we want to maximize just the S1. So here is S2 equal I, and this is O2. So we can write this one as our V2I. So this probability is actually our V2I, and then this probability is our observation 3 state 3 equal K. So that means this one, and this probability is our probability of state 3 equal K and S2 equal I. So probability of state 3 equal K, S2 equal I. Okay. So max over I. Max over I. So max over I is this. So that means V3 of K equal this V3 of K. V3 of K we can rewrite as this one. This is V2 of I. Probability of observation 3 given state 3 equal K. Probability of state 3 equal K given state equal I. So now this one we can rewrite this one as this one. We can see so maximization over I. Maximization over I. I is the variable here. But in this probability of observation 3 state 3 equal K, there is no I. So we can put this one outside of the maximization. We have put this one outside our maximization. And then the problem is max of I, and probability of S3 equal K, S2 equal I. So this probability times the V2I, okay, times the V2I. So V2I. So V3 of K equal probability of observation 3 given S3 equal K, and max of I, probability of S3 equal K, S2 equal I, and V2I. Okay. So that means V3 of K is equal probability of observation 3 S3 equal I, and max of state 3 equal K, state 3 given state 2 equal I, and V2 equal I. If this one is V3, then can we write the V2? Because to know the V3, we have to calculate the V2 also. Then using this similar fashion, can we write the V2? V2 equal K. So this is V3 equal K. Can we write then V2 equal K? For V3, this is observation 3 and state 3. For V2, we have to consider observation 2 and state 2. Okay. Here x equal I. For V3, this is state 3 equal K. But for V2, we have to consider state 2 equal K. And then this is given state 2, then we have to consider given state 1. I. And instead of V2I, we have to consider V1 of I. That means if V3 equal these probabilities, then if we want to find out the V2, then we have to consider these probabilities. Now from here, can we write V1? V1 equal K. Then what will be the V1 equal K? It will be probability of, as the V2 here, so we have to consider probability of observation 1, state 1 equal K. Then max I, probability of, this is state 2. So we can see now V1, that means we have to think about state 1 equal K. Then given this is state 1, then we have to consider state 0 equal I. Then here is the V1, then we have to consider V0 I. But we know that actually there is no state 0 because we have started from day 1, not from day 0. Okay, started from day 1, not from day 0. This is the case. Okay, observation 1, we have state 1. That means day 1, the observation is rain. So there is no day 0. Okay, there is no day 0. So that's why actually from here we can see we cannot get the state 0. So that means this part we have to omit. And then this is the V0 of I. So there will be no V0 because state 0, there is no state 0. So now this probability S1K given S0 equal I, actually it will be just only probability of state 1 equal K. Now we can see here, this is the variable, that is maximization over I. but we can see there is no I in this part. Okay, in this part there is no I. So actually there is no maximization of I also. Okay, there is no impact of maximization of I there. So it means V1 of K equal probability of observation 1 given S1 equal K and probability of this part. Okay, this part is S1 equal K. S1 equal K. So this one will be our V1 of K. So if we closely observe this, then we can see what is it? This is the probability of observation given state. Okay, state equal K. Probability of observation given state equal K. This is emission probability. This is our emission probability. And from the model, we know the emission probability. Okay? This is emission probability of observation 1 and state 1. And what is it? This is actually our initial probability. That is probability of state 1 equal K. So from the model, we know the initial probability and we also know the that is emission probability. So as we know both of these probabilities, we can find out P1 equal K. So if we know the P1 equal K, then we can put the value of P1 equal K here. And then what is there? Again, this one is our transition probability from state 1 to state 2. Transition probability from state 1 to state 2. So we know the transition probability from our model. And what is it? This is actually our emission probability. Okay, emission, and we also know the emission probability. So that means if we know the transition probability, emission probability, and know the V1 equal K, then we can know the V2 equal K. And then this V2 equal K, we have to put it here. And then this is the transition from state 2 to state 3, the probability of that. We will get this one from the model. And then this is the emission probability. Then we will get the V3 equal K. Okay, V3 equal K. So if we know the V3 equal K, V3 equal K, if we know the V3 equal K, that means we know these values. We know these values. Now we have to take the max K, okay, max K. So that means for high atmospheric pressure or maybe for low atmospheric pressure, we will get the maximum. So for high atmospheric pressure or low atmospheric pressure, for which value we will get the maximum, we need to find out that. Then that will be our day three state. And then we will trace back to day 2, and that means for this highest value of K, whether for V2, which value of K is responsible for. Okay, that will be our day 2's state. And to get this maximum, which value of K of V1 is responsible, and that will be considered as our day 1's state. Okay, so that's why the Viterbi algorithms, these variables V is our Viterbi. Okay, Viterbi variable. And now we can see that is the algorithm is this one. V1 of K is probability of observation 1 S1 equal K and probability of S1 equal K. Here is this. For all K, we have to find out. Okay, for all K, that means for all states. In case of our weather model, we have to consider K equal high atmospheric pressure and low atmospheric pressure. And then iterate, we have to iterate over 2 to T. So T is the length of the sequence. Okay, length of the sequence. That means in our case, rain, and dry, day 1, day 2, and day 3. So capital T equal 3 in our case. So day 3 up to day 3. So that means if we know the V1, then we have to find out V2, and in this way, V3, V4, V5. Okay, but in our case, capital T is 3, only day 3 up to day 3. So here is the 2 and then 3. How to find out that? V2 at first we have to consider the V2k, and V2k will be probability of observation 2 given S2 equal k, and max of probability S2 equal k, S1 equal I, and here is there is Vt minus 1. So 2 minus 1, this one will be the 1. And we know the V1 from here. V1 from here. Then we will get the V2 t equal 2. Similarly, we have to increase the t and now consider the t equal 3. So to find out the t equal 3, we have to consider observation 3, state 3, and then state 3 and state 2, and here V2. As we know the V2 from our previous iteration, so we can put the values here to find out the V3. Okay, when we got the terminal condition, this is the max, then we have to find out for which value of k we will get the maximum VTK. Okay, so based on that, we will get the observation, the state of our last day. Last day is day 3 in our case, and then we have to trace back to previous state and previous state to find out our state sequence. Okay, state sequence using the Viterbi algorithm. Now actually we want to solve a problem using our Viterbi algorithm. Let's say we want to solve this problem, this one, rain, rain and dry. What will be the most observable sequence for this? Utilizing our given HMM model. Okay? Then where is our HMM model given? So this is the model that is given HMM model. So consider this one is our given HMM. I want to copy it first. Okay. So based on this model, we want to find out the probability of, or we can say rain, rain and dry. Okay. So that means rain, rain and dry. What will be the observation sequence for that? Rain, rain and dry. Our observation sequence is rain and then rain and then dry. That is first day, second day. This is our OB1, that is O1, and this is our O2, observation on day 2, and observation of day 3 is this. And we want to find out the corresponding states, okay, corresponding states. Corresponding states, that means observation 1, whether the atmospheric pressure is low or high. Similarly, for observation 2, whether the atmospheric pressure is low or high. Similarly, for day 3, whether the atmospheric pressure is low or high. So we want to find out the most probable sequence using our Viterbi algorithm. So what we have to know, what we have to do according to the algorithm, at first we need to find out the V1 of K for all K. K is what? K is the possible states, okay? In our K, how many states are there? The K is our possible states, but in our case, the K is two kinds of states, okay? One is high atmospheric pressure and another one is low atmospheric pressure. K can be high atmospheric pressure, K can be low atmospheric pressure. So that's why I consider that, okay, V1 of low, we want to find out this. So for V1 of low, according to our algorithm, whatever we have derived so far, V1 is observation 1 and S1 equal K. Okay, you can see this P1 equal probability of observation 1 and S1 equal K. What's our observation 1? Observation 1 is R. Okay, that is rain. Probability of rain given S1 equal K. S1 is what? State 1. So state 1 equal K. So we consider the K equal what? K equal L. Okay, so this is L times probability of state 1 equal K. K is what? Initially we have considered K equal L. So here L. So it means from here probability of rain given L, low atmospheric pressure, and probability of low atmospheric pressure. From our model, from this model, you can see probability of rain. Probability of rain given low atmospheric pressure, it is 0.6. So this is 0.6 times probability of low atmospheric pressure. So probability of low atmospheric pressure, this is initial probability, low atmospheric pressure is 0.4. 0.4. So it means we will get 0.24. This is our V1 of L, low atmospheric pressure. We have to find out the V1 of H also. That is high atmospheric pressure, where K equal H. Then it will be, according to our repeated algorithm, it will be the probability of observation 1, and observation 1 is R in our case, given S1 equal K. S1, this time we have considered K equal H. Okay, so here is H. Given probability of S1 equal K, so this time we have considered K equal H. So here is probability of R given H, and that is rain given high atmospheric pressure. So rain given high atmospheric pressure, this one is 0.4. Okay, so we have to consider this is 0.4 times probability of H, probability of high atmospheric pressure. So probability of high atmospheric pressure is what? Probability of high atmospheric pressure is 0.6. Okay, so here is 0.6. .6. So then it will be 0.24 again. Okay, 0.24. Now, as we know already the V1, then we have to find out the V2. We have to find out the V2 for V2 equal V2L. So V2L will be, you can see this is probability of observation 2 given S2 equal K. So probability of observation 2. So for observation 2, you can say observation 2 is also our rain here. Okay, rain R. R is rain. Observation 2 is also rain given state 3 equal K. So state 3 equal K. So this time we have considered K equal L. So L here. And then max I, okay? Max I, state 2 equal K and S1 equal I and V1 I. So that is max I. The I can be again low atmospheric pressure and high atmospheric pressure. So we have to consider max, for which value of I we will get the maximum. I can be low atmospheric pressure and high atmospheric pressure. So we have to think about the max. If we consider I equal L first, okay, L at first L, then probability of state 2 equal K. So state 2 equal K. K, we have considered K equal L. So L, low atmospheric pressure. State 1 equal I, and I also we have considered I is also L, times V1I. Okay, so V1 I, we have considered I equal L. Okay, this one. We also, now we have to consider I equal H. Okay, I equal H. Then it will be probability of now state 2 equal K. So state 2 equal K. K equal what? K equal L. Given state 1 equal I. So this time we can consider I equal H. So here is H times V1 I. V1 I is H. I is H. Okay, so that means between these two, which one is maximum? For which value of I we will get the maximum? So then we have to put the values of these probabilities. Probability of R given L. Probability of rain given low atmospheric pressure. So probability of rain given low atmospheric pressure is 0.6. Okay, so this one is our 0.6. Then we have to apply the maximization. Okay. The maximization. I, low atmospheric pressure and high atmospheric pressure. And probability of low given low. The probability of low given low, the transition probability, low given low is 0.3. So this is 0.3, 0.3. And V1L. What's the value of V1L? This is V1L. V1L is 0.24. So 0.24 for this one. And another one is this probability, okay? Probability of low given high. Just put a semicolon here. And probability of low given high. Probability of low given high. Probability of low given high. So probability of low given high. That is high to low. Okay. So probability of low given probability of low. This is the low given high is 0.2. 0.2 is 0.2 times V1H. So V1H is what? V1H is 0.24. 0.24. So now we can see from here we can write this one as 0.6 and then max I equal L and H. 0.3 times 0.24. It will be 0.72. 0.072. 0.072. And this is 0.0 0.48. Okay, so 0.072 and 0.48. Between these two, which one is maximum? We can see that this one is maximum. Okay, this one is maximum. Actually, this maximum is from I equal L. So that's why we have to note it down that the maximum is 0.072, but we got the maximum from I equal L. So here is 0.6 times 0.072. Okay, 0.072. So that means we will get 0.432. 0.432. So this one is our V2L. Similarly, we have to find out the V2H also. V2H. So for V2H, that means the value of K is now we have to consider H. So that means the equation will be V2H, the equation will be V2H समान probability of R given L. Okay, so instead of L, and now the K equal H. Okay, so K equal H. So here in this case we can see S2 equal K. Okay, so S2 equal K, so that means K equal H. So we have to consider this is instead of L, we have to consider H. Then probability of L given L. So in this case, we can see from our Viterbi algorithm, probability of S2 equal K given S1 equal I. So probability of S2 equal K. So that means now the K is H. Probability of H. And V1 I. So I we have considered initially L. And now here is L. This one is H actually. And V1 H. Okay. Between these two, which one from which one we will get the maximum. Okay. Then now we can write it. Probability of R given H. From our model, probability of R, probability of rain, given H is high atmospheric pressure. So for high atmospheric pressure, this one is 0.4. So we will get here 0.4 times the maximization the maximization of our I equal LH. Then probability of H given L. Probability of H given L. H is high atmospheric pressure given the low atmospheric pressure. So given the low, that means low to high is 0.7. 0.7, and then V1L. So V1L is 0.24. Okay, so this one 0.24. Then now we have to consider this probability of H to H, high to high. The probability of high to high is 0.8. So that means 0.8. And V1 of H is also 0.24. So it means 0.4 maximization over I equal LH. So 0.7 times 0.24, 0.7 times 0.24, 0.168, and 0.8 times 0.24, 192, 0.192. So between these two, which one is maximum? And then we can see the maximum is 192, and this 192 is from I equal H. Okay, I equal H. So it means we have to write 0.4 times 0.192 times 0.4 equal 0.768. 0.768. So this is our V2H. Okay, V2H. So we already determined V2L and then V2H. Similarly, we have to determine V3 of L. Okay, V3 of L. Then how to compute the V3 of L? Okay. So V3 or L. So according to our algorithm, we can see V3, it is observation 3 and S3 equal K. V3, it is observation 3 and S3 equal K. In our case, what's the observation 3? The observation 3, this one is our observation 3. Observation 3 is our D, a dry. So observation 3, so for V3, according to our algorithm, observation 3 and S3 equal K. So observation 3 is dry. So instead of R, we have to think this one. This is our dry. Given, at first we have to consider the K equal L. So here is L, max. Then S3 equal K. So S3 equal K. So S3 K is our L. And then S2 equal I. So here's the S2 equal I. I initially we can consider I equal low. So here is low. And V1 L, okay, and V1 L, V1 I. So V1 low. And then we have to consider also our there is probability of for I equal L. Now we have to consider I equal H. So that is our L given H, V1H, okay, V1H. And for that, this probability, we want to find out the value for that from our model. There is probability of D dry given low. So probability of dry, this is the probability of dry given low atmospheric pressure. So this is 0.4. So here is 0.4. Max of I can be L or H. Now, the first part, this one, the probability of low given low. So probability of low given low is 0.3. So here is a 0.3. And this time, this is not the V1, actually V2. We have to consider V2. This is also V2. Okay. But V2L, we have to consider V2L. V2L, this is our V2L. V2L is equal 0.0432. 0.0432. It will be 0.0432. Okay, now we have to consider this probability from our model. We can see probability of L given H. Probability of L given H. This probability of low atmospheric pressure from high atmospheric pressure is 0.02. So 0.2. So this is 0.2. And V2H. So here is the V2H. V2H is this one. 0.0768. Zero point 0768. Okay, now if we want to continue, it will be 0.4 max over I can be L, can be H. Which one maximum between this 2.3? So 0.3 times 0.0432. 0.0432 equal 0.01296. 0.1296. And this 1.2 times that is 0.2 times 0.07 0768 0.01536 0.01536. Between these two, we can see this one is greater, 0.01536. This one is actually from H equal, from H. It is 0.4 times 0.01536. 0.4 006144 00614 and 4. Okay, so this is our V3L. Similarly, we have to find out the V3H. V3H. So if we want to find out V3H, so V3H will be V3H will be V3 of K. So observation 3, S3 equal K. So observation 3 in our case is D, okay, dry. So that's why instead of rain, we have to say here dry. And K is, this time K is H. So K is H. Max probability of S3 equal K, okay. So here is probability of S3 equal K. So K is our H. Here is H given S2 equal I. So I is, we can consider initially the I is L. That's why here L. And then this is V2L. And then we have to consider I equal H. So I equal H here. And V2 equal H. V2H. Dry given high, this probability we have to find out from our model. Our model is here. Dry given high. So dry given high is 0.6. That means this one will be 0.6, 0.6 times max over L and H. In this case, probability of high given L from our model, probability of high given L. So that means probability of high given L is probability of high is 0.7. So here is our 0.7. And then V2L. Okay, what will be the V2L? In V2L already we got the V2L, V2H, and V2L is 0.0432. 0.0432. 0.0432. 4, 3, 2. And then probability of high given high, according to our model, probability of high given high is 0.8. So here is the 0.8, and V2H, this is V2H, and it is 0.0768. Zero, 7, 6, 8. Okay. And this one will be 0.6 times. Between these two, which one is maximum? Okay. So at first we have to compute. Here's the 0.7 times 0.0432. 0.0432. 03024. 03024. 03024. And another one is 0.8 times 0.0768. It is 06144. 06144. Between these two, which one is maximum? We have to identify that. L and H. There is 0.3 and has 0.6. That means this one is maximum, and actually this one is from our. This one is from H. So I equal H. Zero 0.6 times 0.06144. Point 6 equal 0.36864. 0.36864. So 0.36864. 0.36864. Zero 36864. Okay. So that means V3H we have determined 0.036864, and here V3L is 0.006144. So 006144 and 0.36864. That means between these two, which one is greater? Between these two, this one is greater. Okay? This one is greater. That is for from our V3H is greater than V3L. So which one is maximum? This one is maximum. So what's the value of K of the maximum? This is our H. So V3H, that means this one is maximum. So the last state, as our observation, the last state for the rain and dry. The last state, that last day, the observation 3 day, and this one is from H. The state is high atmospheric pressure on that day. Now we have to find out for this. So what we have to do, we have to trace back. Trace back means this is the largest value we got for V3H. For V3H, to get the V3H, which value of I we have to consider? You can see this one is maximum. Okay, this one is maximum. On that case, we have considered the H. So that means that's why to get the V3H, this one has the maximum contribution. So that means this one is generated from H also, this H. So on day 2, you have to consider this. Okay, you have to consider this. And this one is actually from here, this one is actually from V2H. Okay, V2H. That means this value is from V2H. So we have to go back to the V2H. Here, this is V2H. And for the V2H, which one is maximum? This one is maximum. And this maximum we got from where? For this value of H. Okay, for this value of I, the H. So that means we have to write it H here. Okay, we have to write the H here. Actually, this V2H. So here this V2H is this value we got from here. That is, this value is from our V1H. Okay, the V1H. That's why we have already written the H. But in V1H, you can see V1H, there is no maximization. Okay, no maximization. So that's the end. That's the end. So it means these are the state sequence. So without now we can see that this is the answer. Okay. This is the answer. That means we only know the observation sequence and the model. Then based on the model and this observation sequence, we can find out that the atmospheric pressure on day 1, that is for the observation 1, is high, and atmospheric pressure of day 2, that is from observation 2, is high, and atmospheric pressure on day 3, that is on the dry day, it was also high. Okay? The high, and high. So this is the sequence. So this is how the hidden Markov model can find out there is a hidden state sequence if we know the observation sequence and if we model the problem using hidden Markov model. So that's all in our today's lecture. So do you have any question or queries?
স্যার আমাদের স্লাইডটা দিয়ে দিলে ভালো হতো স্যার।
হ্যাঁ, ঠিক আছে, স্লাইডটা দিয়ে দিব, লেকচার নোটটাও দিয়ে দিব। ওকে, অন্য কোনো কোশ্চেন আছে?
স্যার একটা প্রজেক্ট রিলেটেড কোশ্চেন ছিল স্যার। স্যার আমাদের হলো গ্রুপে হলো 5 জন, যদি একটু কনসিডার করতেন স্যার ভালো হতো।
আচ্ছা, ঠিক আছে, নো প্রবলেম।
আচ্ছা তাহলে স্যার আমরা 5 জনই প্রেজেন্ট করব।
ঠিক আছে।
স্যার আমি স্যার প্রজেক্টটা মানে অলরেডি করে ফেলছি একা একাই। আমি কি একা করতে পারবো স্যার, মানে পুরাটা?
হ্যাঁ, একা করতে পারবো।
ওকে স্যার, থ্যাংক ইউ স্যার।
স্যার আমাদের আর কি কি টপিক বাকি আছে?
তোমাদের তো এবার সেমিস্টার খুব শর্ট, ঠিক না? যার কারণে আলটিমেটলি আমাদেরকে দৌড়াতে হচ্ছে আর কি, বুঝছো? তো টপিক প্রত্যেকটাই কভার করতে হবে, যেহেতু তোমার ওবি সিলেবাসের আলটিমেটলি টপিক আছে সবগুলাই। তো এখানে আরো 2টা টপিক বাকি আছে আর কি আমাদের। তো সামনে 2টা লেকচার আছে, ওই 2 দিনে 2টা টপিক শেষ হবে। আমাদের সিলেবাস যেটা দেয়া আছে ওইটা দিয়ে দেখো তুমি যে 2টা টপিক বাকি আছে।
স্যার রিইনফোর্সমেন্ট লার্নিং এর স্লাইডটা একটু দিলে ভালো হতো স্যার।
একটু দেয়া আছে না অলরেডি?
জি স্যার, রিইনফোর্সমেন্টটা দেওয়া আছে স্যার।
দেওয়া
দেয়া
আছে,
আছে,
আচ্ছা দেখতে হবে এটা।
আজকে স্লাইডটা দিব আর লেকচার নোটটা দিয়ে দিব আর কি, ঠিক আছে? ওকে, আচ্ছা এখন আমাদের হচ্ছে নেক্সট ক্লাসে তো তোমাদের প্রেজেন্টেশন আছে, যাদের একটা কুইজ হচ্ছে নিতে হবে। তো কুইজটাও হচ্ছে কোন একটা টপিকস এর উপর, যেমন রিইনফোর্সমেন্ট লার্নিং টপিকস অথবা এই টপিকস এর উপর। আচ্ছা আমি অ্যানাউন্স করে দিব কোন টপিকস এর উপর কুইজ হবে আর কি। এটা শর্ট কুইজ হবে আর কি, তো 10 মিনিট।